So, in the yesterday's class, we have studied about the experiments that was done by the scientist, and it was said that when we have a uh, um, closed system, we cannot obtain the we can obtain the equilibrium in the closed system, but if we have open system, we cannot obtain the equilibrium at all. So for that, we have done an experiment, and we have seen that whenever we keep the system open, generally we get the liquid evaporate. We even observed that so we tried with the various three liquids, and we have observed that the liquid in all three different type of liquid disappears, and this disappearance of these all liquids is depending upon the few of the very important things. Let us see uh, the disappearance of the liquids, and the time taken for the complete evaporation depends upon the nature of the liquid, amount of the liquid, and the temperature. When watch glass is open to the atmosphere, the rate of evaporation remains constant, but molecules disappeared into the large volume of the room. So by this experiment, we understand that it is not possible to reach equilibrium in an open system, and equilibrium can be established only in the closed system. That is what we understand. Then, my dear students, we have studied the definition of the boiling point, that for any pure liquid, the atmospheric pressure, that is 1.013 bar, and the temperature at which liquid uh, vapors are at equilibrium with the liquid. This temperature is known as the boiling point of that liquid, and point of the liquid depends upon the atmospheric pressure and the altitude of the place where the boiling point is measured. Then, my dear students, we have studied about the solid vapor equilibrium. For that, we have understood the liquid equilibrium that is established for iodine solid and iodine vapor. So, iodine solid, if it is kept into the transparent um, vessel, which is a closed vessel, the vapor of iodine is formed, and thus the intensity of color slowly increases. At some point of time the intensity of color of iodine becomes stable, and now it does not increases, and this is how we can say that there is a equilibrium established uh, between the violet vapor of our iodine and the solid iodine. Let us look at some of the more examples for this kind of equilibrium. So there are a few more examples that we can easily understand. The other examples are the equilibrium that has been established between the camphor solid and camphor vapor. Same way, we can have the another example like the NH4 solid and NH4 vapor. So all those substances which evaporates, we can see such examples. Even we can see into the naphthalene. We can even see the same kind of equilibrium established between the solid carbon dioxide, that is called dry ice, and carbon dioxide gas. Now, my dear students, we want to study about the equilibrium involving dissolution of solid or gases in the liquid. So let us understand how the dissolution of solid or gases takes place into the liquid, or how the various types of solutions can be formed. So first we should understand about solids in liquids. If we make saturated solution of sugar, that is your C12H22O11, we are talking about sucrose. Sugar in which no more solute can be dissolved at given temperature, we considered it as a saturated solution, because at given temperature no more solute can be dissolved into this solution. Now if we cool the solution, what happens? crystals of sugar participates out from the solutions. So when we cool the crystals which were dissolved into the saturated solution, they crystallize out and turns out to be solid into the solution itself. The concentration of solute in saturated solution depends upon the temperature. So if we cool it, the crystals of solid crystallizes out, and this is how we can say that the concentration of solute in saturated solution depends upon temperature. In a saturated solution, there is a dynamic equilibrium between the solute molecules in the solid state and the solute molecules in the solution. So there is always an equilibrium established between the solid molecules which are present as a crystals or in the solid form and which are dissolved into the solutions. So those solid have uh, solids as a solvent, sorry, solids as a solute in solution. So these two solids which are either available as a crystal or they are present into the solution, there is an equilibrium established between these two type of solid, whether they are crystals or they are available as a solute into the solutions. The dynamic nature of equilibrium is confirmed with the help of the radioactive sugar. So you can understand that there is an equilibrium established between sugar which is solid and sugar which is present in the solution. Now from outside, my dear students, if we introduce some of the radioactive sugar. So instead of just writing C12H22O11, C12H22O11. Now we will write it as a radioactive, so we will put star on this. So this sugar which is having star is radioactive sugar. Now this radioactive sugar, as it was involved into the equilibrium disturbs, and after some time again the equilibrium is established. We can see that both the type of sugars, whether it is sugar solid or whether it is sugar present into the solution, both types of sugars now have radioactive sugars present in them. That means when we have introduced this uh, radioactive sugar, this radioactive sugar which was initially solid, that has dissolved into the solution, and this is how even the solution has got radioactive sugar present in them. That means at equilibrium, even the process of dissolution of sugar into the liquid or sugar into the solvent has not been stopped, but it was, the concentration remains the equal and the rate of dissolution is equal to the rate of the crystallization, and that is why at equilibrium both the processes of dissolution as well as the crystallizations are going on, and we find that there is an equilibrium established and their concentration remains constant. Now if we introduce some radioactive sugar in the equilibrium mixture, we realize that after some time the radioactivity is observed in both solid sugar as well as sugar into the solution. It shows that at equilibrium, dissolution and crystallization processes are in continuous motion and they do not stop at all. The ratio of the radioactive to non-radioactive sugars, the ratio of radioactive to non-radioactive sugars molecules increases till the equilibrium is not established. At equilibrium, the ratio turns out to be constant. So solely the ratio of sugar which was dissolved increases, and when again the new equilibrium has been established, then the amount of sugar present into the solid and the amount of sugar present into the solution as a solute becomes constant, and then even the radioactive sugar ratio does not change, it also maintain itself constant at equilibrium, please remember. Now my dear students, we want to study about the gases in liquids. So you might have drink some of the cold drinks where you have soda water or water containing carbon dioxide. This is the best example by which you can understand this situation. So we are talking about this like So when a soda water bottle is opened, some of the carbon dioxide gas dissolved in it fizzes out. Fizzes out means it comes out by making some sound, and as this sound has been produced, we call it as a fizzes out. So the gas dissolved in the soda comes out rapidly. The phenomena um, arises, this phenomena takes place, the phenomena arises due to the difference in solubility of carbon dioxide at a different pressure. So this phenomena takes place due to the difference in solubility of carbon dioxide at different pressure. At different pressure, the amount of carbon dioxide that can be dissolved into the water is different. That is what it simply means, and that is why the soda bottle is closed at high pressure. When bottle is closed, there is an equilibrium between the molecules in the gaseous state and the molecules of gases dissolved in the liquid. So please remember that when soda bottle was closed, there is an equilibrium established between the molecules in the gaseous state and the molecules of gases dissolved into the liquid under pressure. So when bottle is closed, we can say that there is an equilibrium of CO2 gas and CO2 present into the solution. This equilibrium is governed by Henry's law. Now let us study about the Henry's law. Please remember, my dear students, this Henry's law is very important for us. So I wish you learn this. The statement, specially the Henry's law, which states that the mass of a gas dissolved in a given mass of solvent at any temperature is proportional to the pressure of the gas above the solvent. Please remember, this is a very simple statement to understand. The mass of a gas dissolved in a given mass of solvent at any temperature is proportional to the pressure of the gas above the solvent. Once again, the mass of a gas dissolved in a given mass of solvent at any temperature is proportional to the pressure of the gas above the solvent. The amount of gas dissolved in solvent decreases with increase in solvent. The amount of gas dissolved in a solvent decreases with increase in solvent. So, um, once again, let me read it for you so that you can understand it well. The amount of gas dissolved in solvent decreases with increase in the solvent. So if you increase the solvent, then the amount of gas that is dissolved in it can be increased. I think the amount of gas dissolved in solvent decreases with increase in temperature. It should be here. Please make sure that you make these changes in your notes even. It should be temperature. It should be temperature over here. So the amount of gas dissolved in a solvent decreases with increase in temperature. If you increase the temperature, the amount of gas dissolved will also be increasing. Uh, the soda water bottle is sealed under pressure of the gas when its solubility in water is high. The soda water bottle is sealed under the pressure of gas when its solubility in water is high. So, my dear students, soda water bottle is sealed under pressure, so under high pressure, and that is why at high pressure the solubility of gas in water is high. As soon as the bottle is opened, some of the dissolved carbon dioxide gas escapes to reach a new equilibrium condition required for the lower pressure. As soon as the bottle is opened, some of the dissolved carbon dioxide gas escapes to reach the new equilibrium conditions required for the lower pressure. So initially, if there is an equilibrium between the carbon dioxide gas and carbon dioxide dissolved into the solution, then when we open the bottle, the equilibrium disturbs, and then again there will be an equilibrium established between the carbon dioxide that is dissolved in water and it is available into the atmosphere. Please remember, my dear students, that there is some carbon dioxide which is dissolved into the water uh, due to the atmospheric pressure also. So as soon as the bottle is open, some of the dissolved carbon dioxide gas escapes to reach equilibrium conditions required for the lower pressure. Now the lower pressure is 1 atmospheric pressure. So still the pressure is available on the carbon dioxide gas. So carbon dioxide gas still remains dissolved into the water, but the amount of carbon dioxide that is dissolved in the water is decreased, and again a new equilibrium can be established. The lower pressure is equal to the partial pressure of the gas in the atmosphere. So the new pressure is the partial pressure of the gas that is present into the atmosphere. The above is the reason why soda water in the bottle, when left open to air for some time, turns flat. This is the reason why the amount of carbon dioxide gas present into the soda water is decreased, and sometimes we feel that there is no carbon dioxide gas present into the soda water. This is what it happens because the pressure above the soda water decreases. Here the meaning of flat means without carbon dioxide. So after some time we feel that the amount of carbon dioxide dissolved into the soda water has been decreased, and the water become flat. Flat means like water only. We don't feel the soda inside it when we drink it. That is why we have used the word flat. We can conclude that for solid liquid equilibrium, there is only one temperature, that is called the melting point, at 1 atmospheric pressure, at which two phases can exist. If there is no exchange of heat with the surrounding, the mass of the two phases remains even constant. So what remains constant during the solid liquid phase transformation or solid liquid equilibrium? We can now say that first thing that remains constant is the temperature, and second thing, if there is no exchange of heat, the mass of the reactants and products, or mass of the solid and liquid, also remains constant. Let us study about the other equilibrium and understand the various things or various properties that remains constant at various kind of equilibrium. For liquid vapor equilibrium, the vapor pressure is constant. Please remember that for the liquid vapor equilibrium, the vapor pressure remains constant. Same way in the next case, for dissolution of solid in liquids, the solubility is constant. For dissolution of solid in liquid, something that remains constant is known as the solubility at given temperature. Same way for dissolution of gases in liquid, the concentration of a gas in liquid proportional to the pressure, that is concentration of the gas over the liquid. So that is what the partial pressure or the pressure remains constant when there is an equilibrium between the gas dissolves in liquid. So these are the properties that remains constant. Let us revise them by using a table, that what remains constant at what time. See, for the liquid vapor pressure, we have the partial pressure pH2O, that is the partial pressure of vapor remains constant at given temperature. For solid liquid kind of equilibrium, melting point remains constant. If there is no heat exchange, mass also remains constant. When solid and solution equilibrium is established, the concentration of solute in solution is constant at given temperature. And when gas gas and gas in solution equilibrium is established, you can say that uh, gas remains in the aqueous solution and gas remains in the gas form is constant. That means the mass of gas dissolved in the solution remains constant, and mass presence in the gaseous form remains constant. So their concentration, the concentration of both the type of gases remains constant. And if you have, suppose you think about carbon dioxide gas and carbon dioxide aqueous, then the ratio of the mass of the carbon dioxide gas in the aqueous solution and carbon dioxide gas available as a gas, this ratio remains constant. So this ratio remains constant when it comes to the gas and aqueous solution equilibrium. So these were the important points, my dear students. Now we want to study about the general characteristics of equilibrium involving physical processes. So whatever we have studied, actually we are repeating it or we are revising it. Equilibrium is possible only in a closed system at a given temperature. So equilibrium, to establish an equilibrium, we need a closed system. Both the opposing processes occur at the same rate and there is a dynamic but a stable condition. So both the processes, either it is the forward process or reverse process, both the processes takes place simultaneously and the equilibrium is actually dynamic in nature but stable in the form that the concentration remains constant, the rate of forward reactions in rate of the reverse reaction remains constant, and if gases are involved, the partial pressure also remains constant, and that is why we call it as a stable condition. At all measurable properties of the system remains constant. We have seen that there are various properties remains constant at various kind of equilibrium. When equilibrium is established or attained for physical processes, it is characterized by the constant value of one of its parameters at given temperature. These constant parameters are written in the above table. So these parameters which remains constant we have already discussed, but you can understand that whenever there is a equilibrium established, some of the parameters remains constant, uh, which we have studied in this table. I'm talking about this table. Yes, this one. So let us move to the next point. The magnitude of such quantities which remain constant at any stage indicates the extent to which the reaction or reaction has proceeded before reaching the equilibrium. So the magnitude of such quantities, if you measure them initially and when you measure them at equilibrium, you can have an idea that at what extent a particular reaction has forwarded and what type of like whether the reaction goes complete or it goes half or it does not even takes place at all or it takes place in a very small quantity. So by knowing the constant terms, my dear students, we can understand or we can have an idea about the extent of the reactions. Now we want to study about the next point, that is what it is known as the equilibrium in chemical processes and dynamic equilibrium. Till now, whatever we have studied, it was all about the equilibrium into the physical processes. Now we want to study about the equilibrium that can be established into the chemical processes. So let's move forward and understand. For a chemical reaction, we have first to understand the forward reaction. What is forward reaction? A reaction in which the reactants give products is called the forward reaction. Then we have the next term which is known as the reverse reaction. A reaction in which reactants give products is called the, sorry, I made a mistake here. A reaction in which products give reactions. This is again has to be improved. A reaction in which products give reactants is known as the reverse reactions. So a reaction in which products give reactant is known as the reverse reactions. When rates of forward reaction and reverse reaction become equal, the concentration of the reactants and products remain constant. Whenever the rate of the forward reaction and reverse reactions become equal, the concentration of reactants and products generally remains the constant. This is the stage of equilibrium. So when the rate of both the forward and reverse reaction become equal, and if the concentration of reactants and products become constant, this situation is called the equilibrium situation, and this equilibrium is dynamic in nature. So the equilibrium is dynamic in nature. That means both the reactions which is forward reaction and reverse reactions are going on, but the rate of both the reaction become equal, and that is why we do not find any change into the concentration. For better comprehension, means to understand it better, let us consider a general case of reversible reaction. So we have a reversible reaction in which A plus B gives C plus D, and there is an equilibrium established between the reactants and products. With passage of time, there is a accumulation of products C and D and depletion of reactants A and B. That means the concentration of A and B decreases and the concentration of C and D increases. That is what it means. Depletion means decreases, and accumulation means more and more products are formed during this change. This leads to a decrease in the rate of the forward reaction and an increase into the rate of the reverse reaction. So as the number of reactant decreases, the reactants reacting with each other also decreases, and that is why the rate of forward reaction decreases. But as the number of products increases, uh, the rate of products to be converted into reactants increases, and as the time goes on, the rate of forward reaction decreases and the rate of reverse reaction increases, my dear students. Eventually, uh, the two reactions occur at the same rate, and the system reaches a state of equilibrium when the rate of the two reactions, that is the rate of the forward reactions and the rate of the reverse reaction, when they become equal, the system attains the equilibrium. So if we plot a graph, my dear students, if we plot a graph of concentration versus time, you can see here the graph of concentration versus time. You can see that the concentration of the reactants A and B is found to be decreasing. You can see that this is what it is, the continuous decrease, and at some level this become constant. Now there is a straight line. Same way, if you look at the products, the concentration of products were zero at some point, and then it increases, and at this time, now from here it goes stable and they get the straight line. So this is how, my dear students, after this equilibrium has been established, the straight line we can see. Remember that at equilibrium there are two very important things takes place. One thing is the rate of the forward and reverse reaction become constant. Same way the concentration of the reactants and products also become constant, and now they do not undergo any kind of change. That is what you can easily understand from this graph. Now, my dear students, this is not discussed into uh, your textbook, but if we if we uh, if we take out, or if we try to find out the slope for these graphs, my dear students, if we try to find out the slope for this graph, this slope, suppose you have this A, triangle A, B and C. This is point A, this is point B, and this is point C. And this triangle is point P, Q and R. And in that case, the slope you get, how do you write slope? Slope is equal to, in case of this, my dear students, it is AB by BC, AB by BC. And in this case, the slope is equal to PQ by QR. So if you find these values, you will get the rate of the reactions, and when the equilibrium has been established, you will get this flat line, and that is why the rate even becomes same for the forward reaction as well as the reverse reaction. You can see that this is the graph that shows the concentration of the products, and this is the graph with the red line express the concentration of the reactants. If you do not understand anything in this graph, my dear students, you can easily, or you can ask me right now. बच्चों, अगर कुछ समझ में नहीं आ रहा है तो आप लोग पूछ सकते हैं. कुछ पूछना चाहेंगे? क्या आप मुझे सुन पा रहे हैं?
यस सर, सुनाई दे रहा है.
यस सर.
कुछ पूछना चाहेंगे?
नो सर.
नथिंग, कुछ भी नहीं. चलिए दोस्तों,
नो
फिर
सर.
चलते हैं. Okay. Similarly, the reactants Similarly, the reaction can reach equilibrium even if we start with C and D. Similarly, the reaction can reach the equilibrium even if we start with C and D. That means if we started with this way, C plus D, it gives the equilibrium A plus B. So even if we start with the C and D, the same kind of equilibrium can be established between C and D and A and B, or reactants and products. That is, no A and B being present initially, as the equilibrium can be reached from the either direction. So when we start with C and D, there will be no A and B present initially, but later on the A and B will be formed, and then A and B will react with each other to give us the C and D, and then the reverse reaction also starts. And when the reverse rate of reverse reaction and rate of forward reaction become equal, there will be an equilibrium established. And you will or we will observe that when this equilibrium has been established, the equilibrium parameters are also found same, as we have got the equilibrium from A plus B that gives C plus D. And we can say that an equilibrium can be established from both the side, either from the reactant side or from the product side. The dynamic nature of equilibrium can be explained with two examples. So we want to study the dynamic nature of equilibrium, and for that we are going to use two examples. It is very important for you, my dear students, that you understand these examples, and they are going to be very interesting even. Let us move and understand the various examples. Preparation of ammonia by Haber's process. So we want to prepare ammonia by the Haber's process, and for that we have a gas nitrogen that reacts with hydrogen to gives us 2NH3. Haber started with the known amounts of dihydrogen and dinitrogen. So Haber actually started with the known amount of dihydrogen and dinitrogen. You can see this wonderful or very nice graph. Let me explain you the graph. In the graph, my dear students, we have molar concentration on the left side, that is on the y-axis, and time on the x-axis. You can see that the equation was N2 plus 3H2. That gives us, or if there is an equilibrium, we have twice NH3. So this ammonia gas is formed. You can see that initially the concentration of ammonia was 0. Then it has been increased, and then at this point it become constant, and then it gives us the straight line. Same way, the concentration of dihydrogen decreases, and then it gives the straight line. The concentration of dinitrogen even decreases to certain extent, and then it gives the parallel line. So when the equilibrium has been established, all these three lines become parallel to each other because their concentration remains constant, and this is what we can easily understand from this graph. अगर आपको इस ग्राफ में भी कुछ समझ में नहीं आ रहा है तो आप पूछ सकते हैं प्लीज. So when the maintained high, when we maintain high temperature and high pressure at the regular interval, determine the amount of ammonia present. So this scientist Haber has done this experiment, and what he did, he allowed the nitrogen and hydrogen to react with each other at high pressure and high temperature, and at time to time he has tried to find out what is the amount of ammonia that has been produced during this reaction. He maintained an account of the unreacted nitrogen and hydrogen gas too, and plotted a graph of molar concentration versus time, which we have seen, which was as above. The graph shows that after certain time, the composition of mixture of N2, H2 and NH3 remains the same, even though some of the reactants are still present. So all the reactants, nitrogen and hydrogens are present, ammonia is also present, and all these three are present, but their concentration becomes constant. This constancy in composition indicates that the reaction has reached equilibrium. So all the concentration become constant, and we can say that the equilibrium has been established. Now we want to study the dynamic nature of equilibrium. To understand the dynamic nature of equilibrium, we'll have to perform some experiment to understand the dynamic nature of equilibrium. Synthesis of ammonia is carried out with the same starting conditions such as partial pressure, temperature, and known amount of moles of the reactants with a small change. So now we will perform the same experiment, same process. We will maintain all the conditions same like temperature, partial pressure, amount of moles, but we will make a small change. And what is the small change? Instead of H2 gas, that is dihydrogen, we are going to use D2 gas, which is deuterium. So instead of H2, we will use D2 and see what happens. Such reaction mixture reached at equilibrium. So instead of hydrogen, now we have performed the experiment with deuterium, and this reaction also reached to some equilibrium and found, and the composition at equilibrium, that means the amount of gases present at equilibrium, that is the D2, N2 and NH3, this composition at equilibrium found the same. So composition of N2, H2 and NH3 at equilibrium was very same as the composition of D2, N2 and ND3. As it was found in case of N2, H2 and NH3, the only difference was it was N2, D2 and ND3 instead of N2, H2 and NH3. After equilibrium is attained, these two mixtures like N2, H2 and NH3, D2, N2 and ND3 are mixed together and left for a while. So now what happens? We found these mixtures, or we found this both are same. Now we have equilibrium between N2, H2 and NH3 in one vessel. Same way we have an equilibrium established between N2, D2 and ND3, my dear students. Now what happens? We mix both of them. At equilibrium state only, we will mix both these reaction mixtures or both these equilibrium mixtures. That is what I am trying to tell you, that after equilibrium is attained, these two mixtures means mixture of N2, H2 and NH3 and mixture of D2, N2 and ND3 are mixed together and left for a while. So these two mixtures are mixed together and they are even left for a while. When these mixtures is analyzed, it is found that the concentration of ammonia is just the same as before. So even after mixing all this reaction or both these reaction mixtures, after some time if we measure the concentration of ammonia remains constant. When this mixture is analyzed by mass spectrometer, mass spectrometer is a device which can identify the deuterium and hydrogen as a separate species. So now we are going to measure the mixtures with the mass spectrometer so that we can understand the various species present into the reaction mixtures. And when we analyze the mixture with the mass spectrometers, it is found that ammonia and all deuterium containing forms of ammonia like NH3, NH2D, NHD2 and ND3. Once again, when we analyze this mixture with the mass spectrometer, we find ammonia, but apart from ammonia, we can find NH2D, we can find NHD2, we can find ND3. It is found that ammonia and all deuterium containing forms of ammonia, these all are the deuterium containing forms of ammonia apart from NH3. So it is found that all ammonia and all the deuterium containing forms of ammonia are present into the equilibrium mixture. Same way, the dihydrogen and its all deuterated forms like HD and D2 are also present at equilibrium. How this can be formed? So these are formed by the intermixing both the reaction mixtures, and there will be some reaction between the hydrogen and deuterium, between the nitrogen and deuterium, so that all these species are formed. Thus, one can conclude that a scrambling of hydrogen and nitrogen atoms into the molecule must result from a continuation of the forward and reverse reaction in the mixtures. See, the scrambling of hydrogen and deuterium, that means interreaction between the hydrogen and deuterium, at the same time interreaction between the nitrogen and deuterium. That has got possible because when we mix the two equilibrium mixtures, even in that case, there was a reaction that was going on, but the concentration of all the species remains constant. If the reaction had simply stopped when they reached the equilibrium, then there would have been no mixing of isotopes in this way. So if the reaction would have been stopped, my dear students, we would not have got all these other species, but we have got all the other species. It means that the reaction was continuous, the reaction was going on even when the equilibrium has been established. Use of isotopes, that is deuterium, in the formation of ammonia clearly indicates that chemical reactions reach a state of dynamic equilibrium in which the rate of the forward reactions and the rate of the reverse reaction are equal and there is no net change in the composition. So at equilibrium, the forward and reverse reactions are uh, going on continuously. We can even understand that equilibrium can be obtained from the both the side. For first case, whenever we start reaction by taking hydrogen, nitrogen, we get ammonia. Whenever we start reactions between nitrogen and hydrogen, we generally get the ammonia, my dear students. So we get N2 plus 3H2, that gives twice NH3. Suppose at equilibrium we have X mole N2, Y mole of H2 and Z mole of NH3. Now suppose case 2, by taking NH3 we decompose it and form N2 and 3H2. So we will have the reactions 2NH3 that gives N2 plus 3H2, and at equilibrium we will have this Z mole of NH3, X mole of N2 and Y mole of H2. So in both the cases, if you really compare, you will have the same amount of reactants and products available, or same amount of species are available at equilibrium. From this we can say that the moles at equilibrium, mole of N2 is X mole, mole of H2 is Y mole, and mole of NH3 is Z mole. In both the cases, whether you obtain the equilibrium from the reactant side or you obtain the equilibrium from the product side, and this is how we can say that equilibrium can be established from either of the sides. The second example we will study into the next class. Now if you have any doubt, my dear students, you can ask me or we can start the revision. बच्चों कुछ पूछना है तो आप पूछ सकते हैं. बच्चों, क्या आप मुझे सुन पा रहे हैं? आप कुछ पूछना चाह रहे हैं?
नो सर, सुनाई दे रहा है ना सर.
ओके.